Okay, we're moving on to 6.2. 6.2 is how do you use properties of exponents to simplify rational exponents. So in your book on page 420 are properties of rational exponents. Now what you'll notice is the properties of the rational exponents are the exact same properties we learned for general exponents. Okay, they're all the same. The only difference is our exponents are fractions or roots. So all we're doing is applying. For example, the first property here, the product of powers, we add the exponents. Well, here's our example. We're just adding fractions is all we're doing. Okay, here we're multiplying power to a power. We're multiplying a fraction times a power. So in this section we're just dealing with fractional exponents. Some of these problems in this section are fairly challenging. So we're going to break this into 2 days, and there's going to be 2 videos. So this is the first video where we're going to apply these properties to numbers. Okay, there's no variables here. Okay, all we're trying to do is take a numeric expression and simplify it down. So the second video will apply it to variables. Okay, so basically I'm just going to go through some examples for this section and try to cover all the different examples and problems that you'll see. So let's start with this first one. So we got 5 to the 1/3 times 7 to the 1/4 raised to the 3rd power. Now we cannot add these exponents because the bases are different. But what we can do is multiply this power through here. Okay, so this is going to end up being 5 to the 1/3 times 3 is 3/3. I'll just write it as 3/3 times 7 to the 3/4. Okay, and we know 5 to the 3/3 is just 5 to the 1, so I could write this as 5 times 7 to the 3/4. That's how I'm going to leave it. I cannot multiply these two and get 35 because we got this exponent here. Okay. Number 2. Now we get the bases are the same, so we can add the exponents. So this is going to be 2 to the 3/4 plus 1/2. Okay, so 3/4 plus 1/2 is the same as 2/4. That's going to be 2 to the 5/4. Okay, we can leave it like that. If you want, I guess you could write it as a root. But we can leave these as a fractional exponent too. Now what do we do on this one? Our bases are the same. What's the power up here? There's no number, so our power is actually 1 there. So what we can do is subtract 1 minus 1/4. What's 1 minus 1/4? Well, that's 4/4 minus 1/4, so it's 3/4. 3 to the 3/4 on that one. Okay, number 4. Now we got a couple options on this one. We can multiply through the exponents here, or because the exponents are the same, we can divide the bases. Okay, 20 divided by 4 or 5 is 4. So you could write this as 4 to the 1/2 raised to the 3rd power. Okay. Now what's 4 to the 1/2? That's the same as the square root of 4, which is 2. So this is actually 2 cubed, or 8. Okay. Now this one, our base is the same, so what do we do with the powers? We add them. Okay, how do I add 1/8 plus 5/6? Well, we need a common denominator, which is 24. 8 goes into 24 3 times, so that's 3/24. 6 goes into 24 4 times. 4 times 5 is 20. Add the numerator, so you're going to get 12 to the 23/24. That's what you get on that one. Okay, this one we're going to multiply these exponents. Bases are different, so we get 2 to the negative 6/6, which is -1, and 4 to the -1. We know negative exponents, we can put them in the denominator and make it positive 2 to the 1 times 4 to the 1, which is 2 times 4, which is 8. So it's 1/8 on that one. Okay, number 7. Again, this is similar to number 4 up here. Our exponents are the same, so we can divide these. 56 divided by 7 is 8. So this is 8 to the 1/4 raised to the 5th power, which is 8 to the 5/4. Okay. Next one. 4th root of 27 times the 4th root of 3. If our roots are the same, we can multiply the number underneath, the radicand. So we get the 4th root of 81, and the 4th root of 81 is 3, because 3 to the 4th is 81. Okay. Number 9. The roots are the same, so we can divide these. We'll get the cube root of 125. Cube root of 125 is 5, because 5 cubed is 125. Okay, so there's a variety of problems there that should match up with some of your problems you'll get in your assignment. Let's move on to simplifying these roots. Let's refresh our memory on what simplest form means. It means there's no perfect nth power in the radicand, that's the number under the root, and no nth root or no roots in the denominator. So it's similar to what we were doing before, only we're applying it to any root instead of just square roots like before. Now I did write the perfect cubes and perfect square or perfect 4th powers on the side here. 2 cubed is 8, 2 to the 4th is 16. 3 cubed is 27, 3 to the 4th is 81, and then so on here. So those are numbers we could keep going to if we wanted to, but you should recognize those numbers. Okay, so let's start with the cube root of 135. So the question then is there a perfect cube number that goes into 135? Do any of these numbers go into 135? Sure enough, 27 does. So I can break that into the cube root of 27 times the cube root of 5. 27 times 5 is 135. Okay, and what's the cube root of 27? 3. So it's 3 times the cube root of 5 on that one. Okay, look at number 11 here. Now this is subtraction, so we can't just subtract underneath here. But what we can do is try to simplify this. What goes into 54? 27 again. So I can break this into the cube root. I'm going to write it above here. Cube root of 27 times the cube root of 2. 27 times 2 is 54. The cube root of 27 is 3. So this is 3 times the cube root of 2 minus the cube root of 2. So what does that equal? Well, think about this. What would I get if I took 3x minus x? I would get 2x, right? So 3 cube roots of 2 minus 1 cube root of 2 ends up being 2 cube root of 2. That's how you do that. You can treat this like x. Okay. Let's look at this one next. 5th root of 3/4. Okay, now we can rewrite this as the 5th root of 3 over the 5th root of 4. Now because we have a root in the denominator, we want to try to simplify that and get the root out of the denominator. So if you remember, we used to rationalize the denominator. We can do that here too. But what we need to do, and this is a little tricky, is we need to multiply this by something that gives me a perfect 5th power down here that I can get. So I didn't write perfect 5ths, but if I did, just slide 5th, 2 to the 5th is 32, 3 to the 5th is 243, I believe. You can keep going. So we need a number down here that I can take the 5th root of. So can I make this become 32 somehow? What would I have to multiply 4 by here to get 32? Right, it'd be 8. So I want to multiply top and bottom of this by the 5th root of 8. Because the 5th root of 4 times the 5th root of 8 is the 5th root of 32. And then this would be what? The 5th root of 24. So the 5th root of 32 happens to be 2, because 2 to the 5th is 32. And that's the 5th root of 24. So what we've done is we've gotten the root out of the denominator. So that's a little tricky. It's kind of like rationalizing the denominator, but we need to multiply by something that gives me something I can take that root of. Makes it a little bit different. Okay, last problem here. Let's see, we got the cube root of 5, cube root of 40. So the question is, what perfect cube goes into 40? I think it's 8. So you get the cube root of 5 plus the cube root of 8 times the cube root of 5. Because 8 times 5 is 40. Cube root of 5, cube root of 8 is 2. So we got 1 cube root of 5 plus 2 cube root of 5 is equal to 3 cube root of 5. So that's what I would get there. Alright, so that's the first part of section 6.1. These problems get a little tricky, and your homework or your problems in class tomorrow are going to be a little bit of a challenge, but we'll work through them a little bit together, and then the second half of this section we'll apply this to variables.